How does adding resistors in parallel affect the current strength in the main part of the circuit? Here we have 3 circuits which can help us to answer this question. Notice that in all cases we have a 9-volt cell and we have an LED and we have an ammeter which is measuring current strength in the main part of the circuit. But what is different between these 3 circuits is the resistors. In A we only have 1 resistor. In B we have 2 resistors, but they are connected to one another in parallel, meaning that there is a branch in the circuit. All the charge has to flow through the cell, out the positive terminal and round through the ammeter, but then at this point the charge can choose. Some of it goes through this resistor and some of it goes through that resistor, and then the charge joins again, and all of it has to flow through the LED and back to the negative terminal of the cell. In circuit C, there are even 3 branches, so 3 choices that the charges can choose between. So in C, there are 3 resistors in parallel. So we are asking, how does adding resistors in parallel affect the current strength that we measure in the main part of the circuit? Notice that the ammeter is positioned in the main part of the circuit for each of these circuits. That means it's in the part of the circuit where all the charge has to flow. It's not in one of the branches where only part of the charge chooses to flow. We can liken this to 3 water circuits. Here we can see in circuit A, there is only one narrow part to the circuit because there's only one resistor. The wide pipes represent the good conductors. It's very easy for the water to flow there. But the narrow part represents a resistor. It's more difficult for the water and for the electricity to flow through that. Now in circuit B, you can see that we have 2 resistors, 2 narrow pipes. But these pipes are connected in parallel to one another. So some of the water can go through the top pipe and some of the water can go through the bottom pipe as it moves from the right area to the left area of the string. And in circuit C, we have 3 narrow pipes joining the 2 wide sections of the water circuit. Let's speak about the voltage across each of these circuits. Very simply, voltage means push. How hard the battery is pushing the charge through the circuit, around the circuit. In a water circuit, we can think of this like water pressure that pushes the water around in the water circuit. Each of these circuits has a 9-volt cell, or we can say 9-volt battery in it. So that means that in each circuit, the electric charge is being pushed around the circuit just as hard. It's like the water being pushed with just the same pressure in A, B, and C. Let's compare the brightness of the LEDs. If you actually build these 3 circuits, you will see that A's LED is the dimmest and C's LED is the brightest. What does that tell us? That tells us that the current strength through A's LED is low. So not many charges are traveling through that LED every second, giving energy to that LED to convert that energy into light. So it's dim. But in C, the LED is bright. Why? That's because there's a high current strength through that LED. So a lot of charge is traveling through it every second, delivering a lot of energy every second, which it converts into light energy. That's why it's bright. We can see the same point by measuring current strength directly with an ammeter. When you do this, you will find that the current strength in circuit A is 0.36 milliamps. The current strength through the main part of circuit B is 0.73 milliamps, and the current strength through the main part of circuit C is even greater, 1.08 milliamps. So you can see the LED brightness and the ammeter reading, they go together. In circuit A, they are both low. In circuit C, they are both a lot high. And that fits with our pictures of the water circuits. Because can you see that in A, it's more difficult for the water to flow than in C? In C, it's easier for the water to flow because these narrow parts add up into a thicker pipe. So it's not so resistant, it's easier. But in circuit A, there's only one narrow pipe that all the water has to go through, and so that makes it much more difficult. So the water would flow quicker through circuit C than circuit A. Similarly, the electric charge flows around circuit C quicker than it does in A, because when it comes to the resistant part, at least in circuit C, it's got a few paths it can go through, and so then it's easier overall. But in circuit A, there's only one narrow path that all the charge has to squeeze through, and so it makes everywhere very slow. So how does adding resistors in parallel affect current strength in the main part of the circuit? Let's answer this question by choosing either increases or decreases here. Adding resistors in parallel does what to current strength in the main part of the circuit? The more resistors there are in parallel, the easier it is for the current to flow. The more current flows. Adding resistors in parallel increases current strength in the main part of the circuit. And that's because adding resistors in parallel decreases resistance. It makes it easier. And that's why it increases I main. It makes the current strength in the main part of the circuit go faster.